Free radical halogenation is an important reaction in organic chemistry, as one of the few reactions that alkanes can undergo. By the way, if you're watching this video because you thought it had something to do with anarchist hippies and halogen lamps, I'm sorry to disappoint you. In chemistry terms, a free radical refers to an atom with an unshared, non-bonded electron. Free radicals are generally quite reactive and thus useful in this synthesis. Halogenation simply refers in this case to replacing a carbon-hydrogen bond with a carbon-halogen bond in a molecule. Following the trend seen in other reactions, fluorine is the most reactive in free radical halogenation, and iodine is the least reactive. Fluorine is so reactive that the reaction is hard to control, whereas iodine is unlikely to react in most circumstances. Therefore, chlorine and bromine are two halogens typically used in free radical halogenation. We will use monochlorination of methane as an example as we explore the mechanism of this reaction. First, ultraviolet light splits a chlorine molecule to form two chlorine radicals. This is known as the initiation step. The propagation steps follow. A chlorine radical reacts with methane to produce hydrogen chloride and a methyl radical. The methyl radical reacts with a chlorine molecule to produce chloromethane and another chlorine radical. The termination step ends the reaction. In the termination step, two free radicals combine to produce a stable molecule. This can occur in several different ways. Two chlorine radicals can reform a chlorine molecule, a methyl radical and a chlorine radical can form chloromethane, or two methyl radicals can form ethane. The radical can even react with the side of the container as a termination step. Free radical halogenation does not have to stop with the monosubstituted products. In the case of the free radical chlorination of methane, methylene chloride, chloroform, or even carbon tetrachloride can form. One can control which chlorinated compound will be the major product, however, by controlling the initial concentration of chlorine. The more chlorine added, the greater the concentration of the more substituted products. For methane and ethane, each hydrogen is equivalent, meaning that only one monohalogenation product can result. But what happens with longer and more branched hydrocarbons? Obviously, there will be a mixture of products. Let's say we start with 2,5-dimethylhexane and bromine. The unbalanced reaction shows all of the possible products. Now, which one would be the major products? You might think at first that it would be this one, because any of 12 hydrogens could be replaced to make the products. However, you would be incorrect. It is actually this one, even though there are only two hydrogens that could be replaced to form it. Why? Because of principles involving thermodynamics, including reaction kinetics and radical stability, free radical halogenation is a selective process. The reaction occurs fastest for a tertiary carbon, followed by a secondary carbon, then a primary carbon, and finally a methyl carbon. Bromine is also more selective than chlorine, again for reasons concerning thermodynamics. The relative reaction rates for chlorination are 1 to 3.9 to 5.2 for primary, secondary, and tertiary carbons respectively. For bromination, the relative rates are 1 to 82 to 1640 for primary, secondary, and tertiary carbons respectively. Applying math to the earlier example, the product distribution would be roughly as follows: 0.33% 1-bromo-2,5-dimethylhexane, 9.06% 3-bromo-2,5-dimethylhexane, and 90.61% 2-bromo-2,5-dimethylhexane. When either chlorination or bromination will work for the synthesis at hand, organic chemists often choose bromination because it allows for greater yields and a purer product. Does your brain hurt yet? If so, welcome to organic chemistry.